Hello and welcome to part 3, and we are on to the series of solving the previous year question paper held at SIES Graduate School of Technology at the end semester examination. We are on to question number 2A. Question number 2, each sub-question carries 10 marks. So right now on the screen which we see, that question has a weightage of 10 marks. Now let us begin solving this problem. So we got to find out the rank of the given matrix. We are given a 4x4 matrix by reducing it to normal form. Here I would like to give you a heads up that there are two types of forms that we look up in this chapter. So one is the row echelon form, or simply the echelon form, and the other one is normal form. Now if you're dealing with row echelon form, then you are allowed to use only EROs, which stands for elementary row operations, wherein when you are talking about normal form, you are permitted to use both EROs and ECOs, that is elementary column operations as well. So now since this is normal form, we can use both elementary row operations as well as column operations. So we'll be first declaring this matrix as capital A. So let us say that let A is equal to the given matrix. Now since these are 10 marks problems, we are going to have a lengthier solution, and hence I will be writing it down sideways. So please try and understand how you have to write it down in the examinations. So this is the matrix A. Now on this we are going to perform a set of elementary row as well as column operations and try and reduce it to normal form. To recall what is a normal form is a matrix which has a block of identity matrix of order R by R on the top left, and it is surrounded by 0, 0, 0 on its right and the bottom. So since here it is a 4x4 matrix, we could have a block of IR. R could be either 1, 2, 3, or if possible it could be 4 as well. So we are looking out for this identity block. So we do understand that we need a 1 and other entries should be 0 in that particular row as well as column. And likewise, if this is a 1, then the other entries in that particular row and columns should be 0. Now firstly, we don't have a 1 here, so let us generate 1. Now we see here that there is 3 and 2, so 3 minus 2 could possibly give us 1. So we'll perform R2 minus R1, and that is going to affect the second row. So let us write down the other rows first. Now R2 minus R1, so we'll just subtract. So this is going to be 1, 1, 1, 1. Now we have a 1 over here that we'll look up to move on the top. So we'll have a row swap. So next we'll be performing is R1 exchanged with R2. So this is going to give us 1 moved up, the second row coming down, and the other 2 rows as it is. Now we have a 1, which is the pivot element or the leading entry. What we are going to do next is try and reduce the other entries in the row and in the same column containing 1 to be 0. We'll begin with the column entries and reduce them to 0 first. We need to perform elementary row operations on R2, R3, and R4. On R2, we are going to perform R2 minus 2 times R1. On R3, we are going to perform R3 minus 4 times R1. And on R4, we are going to perform R4 minus 9 times of R1. So this is going to give us 1, 1, 1 in the top row. Now the second row, it is R2 minus 2 R1. So this is going to be 0, 1, 2, and 3. Here also we will have 0, 1, 2, and 3, and so in the last row. Now you see that we have a 1, and then following it in the respective column, we have all zeros. Now for the next part, we are going to work on these 3 ones and try and reduce them to 0. They are arranged column wise. So we are going to perform column operations. So we need to perform on C2, C3 and C4. And please make a note that you have to always use the pivot element only. So the pivot element in this case is in column 1. So we'll be performing C2 minus C1, C3 minus C1 and C4 minus C1 on the last matrix. So let us write down the entries column wise. So this is going to become 0, this remains 1. This is going to become 0, this remains 2, 2, 2, 2, and the last one we have got 0, 3, 3, 3. So our first row and first column is clear. Now also we have got the next pivot element, which is 1. Now we are going to make elements on the right of it 0 as well as below it 0. So let's start with row operations again. We need to work on R3 and R4. On R3 we will perform R3 minus R2, and on R4 also we'll perform R4 minus R2. Let us write down the first two rows as they are. Now you see that the rows are alike, so the difference is going to give us straight away 0. No calculations are required here. Now again, you see that the second column is set up. Now we need to reduce these two entries to 0, and we are going to use this as the pivot element. So next we are going to perform on C3 and C4. On C3 we will be performing C3 minus 2 times of C2, and on C4, C4 minus 3 times of C2. So we have got 1, 0, 0, 0 in the first column, 0, 1, 0, 0 in the second column. Now over here we will get 2 0 columns. So if you will look, this is first row and first column, there is a 1. Then second row, second column, we have got a 1, and all other entries are 0. So this gives us the normal form. So we can write down that therefore normal form of A is equal to. Now you will see that we have got an identity matrix block over here, which is of order 2 by 2. So we will be saying that this is equal to I2, and then we'll have 0, 0. Since the order of the identity matrix is 2, so we can conclude that rank of a matrix, which is denoted by row of A, it is also going to be 2. So that concludes the solution. So just be little careful about the things that I told you in the start. If you have a row echelon form, then perform only EROs, wherein if you have a normal form, then you can perform both EROs as well as ECOs. And second thing, always use the pivot element entries only for your EROs and ECOs. Okay, let's move on to the next problem. So here we have question number 2b. It is based on the module complex number, hyperbolic functions and logarithms of complex number. So we are given an equation which says that cos hyperbolic of x is equal to secant of theta, and we are required to verify the three things. So I'll just say that we are given cos hyperbolic of x is equal to sec of theta. Now there are multiple ways to solve this problem. In the first part, you will see that we are interested in the value of x. So you can obtain x by actually implementing the definition of cos hyperbolic, which is e raised to x plus e raised to minus x over 2, and then do simplification, get a quadratic equation, and write down the answer. We are going to use the other one, which involves the inverse hyperbolic functions. So since we are given that cos hyperbolic of x is equal to theta, from here I can say that x is equal to cos hyperbolic inverse of sec of theta. Now we are aware that cos inverse of y, it is evaluated as log of y plus square root of y square minus 1. So here you will see that y is replaced actually by secant of theta. So we can say that therefore x is equal to cos hyperbolic inverse of sec theta, which becomes log of sec theta plus square root of sec square theta minus 1. Now, we are very well aware about the identity relationship between tan square and sec square theta. So, this is going to be square root of tan square theta using 1 plus tan square theta is equal to 1, which gives us x is equal to log of sec theta plus tan of theta. And that is the first part of your problem. Now, moving on to the second part. For the second part, we are looking out for a value of theta. Now, to give you a heads up for this, you will see that in the given question over here, you are interested in e raised to minus x. So, we have got x over here. So, if I call this as 1, so from 1, I can take the reciprocal. Sorry, from 1, I can take the exponent. So, I'll get e raised to x is equal to, and e raised to and log will nullify each other. We will get that this is equal to sec of theta plus tan of theta. Since we are looking out for e raised to minus x, so this is going to be the reciprocal of sec theta plus tan theta. And as we are aware in high school that we can kind of do conjugation over here, so we'll be multiplying and dividing it by sec theta minus tan theta. So in the numerator we have got sec of theta minus tan of theta, while in the denominator we get sec square theta minus tan square theta, and this reduces to sec of theta minus tan of theta. So we have got a value of e raised to minus x. Now it doesn't stop here. You are interested in an expression for theta. So now coming back over here, we can say that e raised to minus x is equal to 1 by cos theta minus sin theta by cos theta. So this is going to be 1 minus sin theta divided by cos of theta. Now another thing, you need a pi by 2 part. So this pi by 2 part actually comes from trigonometric ratios of complementary angles. So we can rewrite sin theta as cos of pi by 2 minus theta, and likewise in the denominator we can write the cos ratio as sin of pi by 2 minus theta, and this can be simplified as cos of alpha divided by sin of alpha, where alpha is equal to pi by 2 minus theta. Using the half angle formula, this is going to be 2 sin square alpha by 2, and in the denominator we are going to have 2 sin alpha by 2 into cos alpha by 2. And there are certain reductions going to take place, so we will be left out with sin of alpha by 2 over cos of alpha by 2, and thus we get that e raised to minus x is equal to tan of alpha by 2. We can say that alpha by 2 is equal to the tan inverse of e raised to minus x, and plugging in back the value of alpha as pi by 2 minus theta, we get that alpha is equal to 2 tan inverse e raised to minus x, and now we will plug in. So we will be getting pi by 2 minus theta is equal to 2 tan inverse of e raised to minus x, and thus we get that theta is going to be pi by 2 minus 2 times tan inverse of e raised to minus x. So that gives us the second part of the proof. Now moving on to the third part, which is this. So we are looking out for tan hyperbolic ratio of x by 2, and we need to show that it is equal to tan of theta by 2. Here we can start with the definition of tan hyperbolic. So by definition, tan hyperbolic of x by 2 is going to be e raised to x by 2 minus e raised to minus x by 2 divided by e raised to x by 2 plus e raised to minus x by 2. And using the reciprocal property for this, we can rewrite this expression as e raised to x minus 1 divided by e raised to x plus 1. Now if you will see, we already have a value of e raised to x over here. So let us mark this as equation number 2 and use this. So we'll say that this is going to be sec theta plus tan theta minus 1 divided by sec theta plus tan theta plus 1, and this follows from equation number 2. Now using the definitions of sec and tan, we can say that sec is going to be 1 by cos, tan is going to be sin theta by cos theta minus 1, and this is divided by 1 by cos theta plus sin theta by cos theta plus 1, and this is going to give us 1 plus sin theta minus cos theta, and in the denominator we will get 1 plus sin theta plus cos theta. Now what we are going to do is we are going to club in 1 and minus cos and 1 and cos. So 1 minus cos 2 theta by half angle formula is going to be 2 sin square theta by 2 plus, for sin 2 theta we can write it as 2 sin theta by 2 cos theta by 2, and in the denominator we will have 2 cos square theta by 2 plus 2 sin theta by 2 into cos theta by 2. From the numerator we can take 2 sin theta by 2 common, and we'll be left out with sin theta by 2 plus cos theta by 2, and in the denominator we can take 2 cos theta by 2 common, and we'll be left out with cos theta by 2 plus sin theta by 2. So as you can see that we can get rid of this bracket and also the 2, and thus we get sin theta by 2 upon cos theta by 2, which is going to be tan of theta by 2. So we started with tan hyperbolic of x by 2 and we got tan of theta by 2. That is what was needed to show in the third part. So thus we have completed all 3 parts of question number 2, which carries a weightage of 10 marks. Now let's move on quickly to question number 2C. So here we have question number 2C. It is based on partial differentiation, and you can see that you are given a function u which consists of 2 parts. One is this and the other one is this. We are told to find the value of this expression involving partial derivatives of first order and second order of u. Now if you will pay attention over here, then this expression is available to us in the corollary of Euler's theorem, while this expression is available to us in Euler's theorem. So Euler's theorem states that if a function is there, let's say u, and if it is homogeneous of degree say n, then so the Euler's theorem states that x into del u by del x plus y into del u by del y is going to be n times of u, wherein the corollary to Euler's theorem tells you that x square into del square u over del x square plus 2xy del square u over del x del y plus y square del square u over del y square is equal to n into n minus 1 times of u. So this is the Euler's theorem. The first one is the Euler's theorem. There's the second one is the corollary to Euler's theorem. So we see that this part is needed over here, wherein this part it is needed over here. Okay, so what we will be doing is we are going to talk about u, we are going to discuss its homogeneity, and then we are going to see whether we can apply the Euler's theorem and its corollary. It can be seen that given u is actually going to be of the form v plus w, where the function u is equal to x raised to 4 plus y raised to 4 divided by x square y square, and it's not u, sorry, it is v, and w is equal to x raised to 6 into tan inverse of x square plus y square divided by x square plus 2xy. We will be first discussing about v, and we will check its homogeneity, whether it is homogeneous, and if yes, then what is the degree of homogeneity. So we start with v of xt comma yt. If we plug in xt instead of x and yt instead of y, we are going to get xt raised to 4 plus yt raised to 4, and in the denominator we will have xt square yt square. So you can see that in the numerator we will have t raised to 4 common, and we will be having the other factor as x raised to 4 plus y raised to 4. Again, in the denominator we will have a product t square into t square, which is t raised to 4 along with x square y square. So we can get away with the t raised to 4, and what is left is nothing but v of x comma y. So from here we can say that v is a homogeneous function of degree n1 equal to 0. Now since no power of t is present here, so we can always say that it is t raised to 0, and that power of t is the degree of homogeneity for v. And likewise, let us talk about the homogeneity of w. So again, same way, so we'll talk about w of xt comma yt. So this is going to be xt whole raised to 6 into tan inverse of xt whole square plus yt whole square, and in the denominator we are going to have xt whole square plus 2 into xt into yt. So this is going to be t raised to 6 into x raised to 6 tan inverse of. Now from the numerator we can again have t square common, and the other factor is going to be x square plus y square, while in the denominator again we can have t square common, and we'll be having x square plus 2xy. So you can see that we get away with this, and we are left out with t raised to 6. Now whatever part is left out, that is nothing but w of x comma y. Now here you can see that the power of t is 6. So we can say that therefore w is a homogeneous function of degree, let's say n2 equal to 6. Since v and w both are homogeneous of respective degrees, we can apply Euler's theorem, which we had stated here, and as well as its corollary, which we have stated down here, to both v and w. So by Euler's theorem we will get that x del v by del x plus y del v by del y is going to be n times u. Now n in this case is 0, so this is going to be 0 times v, that means it is simply 0. Whereas by the corollary we will get x square into second order partial derivative of v with respect to x plus 2xy into del square v del x del y plus y square into del square v del y square is going to be 0 into 0 minus 1 into v, which is again 0. Moving on towards w, we will be getting x into del w by del x plus y into del w by del y is going to be 6 times of w, and by the corollary we will get that this expression is going to be n into n minus 1 into W, which is going to be 30W. Now have a closer look at this expression. So we are interested in the terms which are involving U, wherein whatever results we have got so far, they don't deal with U, they deal with the functions V and W. So let me show you what we are going to do next. So since U is equal to V plus W, so therefore, if I talk about the partial derivative of U with respect to x, this is going to be del V by del x plus del W by del x. And the same is going to happen with partial derivative of U with respect to y. It is going to be del V by del x plus del V by del y. And similar things are going to happen to the second order partial derivatives. So this is going to be del square V over del x square plus del square W over del x square. This is going to be del square V over del x del y plus del square W over del x del y. This is going to be del square V over del y square plus del square W over del y square. So therefore the given expression which we have on the left side, I'll just paste the value here. Now this is the required expression. So therefore the given expression can be written as x square. Now we have a factor here del square U over del x square, and we can use this relationship to rewrite that. So it is going to be del square V over del x square plus, I just write down the other term down, x square into del square W by del x square. Now we have got 2xy, so plus 2xy. Then we need del square U over del xy, which is here. So it is going to be again del square V over del x into del y, and the other term I will write it down. And then we have got y square into del square U over del y square, which we have got over here. So this is going to be y square into del square V over del y square plus y square into del square W over del y square. Now moving on to the first order part, we need x into partial derivative of U with respect to x. So by using this relationship, it is going to be x into partial derivative of V with respect to x plus x into partial derivative of W with respect to x. And the last term is going to be y into partial derivative of V with respect to y. And over here we will have y into partial derivative of W with respect to y. Now we have got all these values evaluated, which are here. So you can see that this is this expression, which is 0. So we can write this as 0 plus. Then we need this expression, x into partial derivative V with respect to x plus y into partial derivative V with respect to y, which is again over here. And that also we have got as 0. So let us write another 0 here. Plus, coming down, we need this expression, and this expression is present right over here, and it has the value 30W. So we can say that this is equal to 30W plus, and the last one is this expression, and we have got it right over here, and it is equal to 6W. So we can say that plus 6W. So this is equal to 36W. You can of course label the expressions as 1, 2, 3, 4 and write it accordingly. Now we have got this to be 36W, and this is the part that we had labeled as W. So this is going to become 36 into x raised to 6 into tan inverse of x square plus y square divided by x square plus 2 into xy. Now you also see that we want to find out this value, the value of this expression when x is equal to 1 and y is equal to 0. So when x is equal to 1 and y is equal to 0, we will be getting this to be 36 into 1 raised to 6 into tan inverse of, so in the numerator we will get 1 square plus 0 square, which will be 1, and in the denominator we will get 1 square plus 2 into 1 into 0, which is again going to be 1. So we have tan inverse of 1, which is pi over 4, and here we have a 36. So on cancellation we are going to get this to be equal to 9 pi. So this is the value of the expression that is asked to us. So with this we complete 3 sub questions of question number 2, each carrying 10 marks. Prepare well for your upcoming examinations. All the very best and happy learning.